So, so before closing the inductance chapter, so we will take couple of more examples, then we will move to the next chapters, right. So, come to this example. So, first thing is that determine that in between one or two, I brought several examples for you, but time constant is of course there, but look at this example figure. I will show you. Determine the geometric mean radius of a conductor in terms of the radius r of an individual strand for A, these 3 equal strands as shown in figure 19a, and B 4 equal strands as shown in figure 19b, right. So, this is your figure 19a and this is your figure 19b, right. So, you have to find out geometric mean radius of this configuration and this configuration, right. Then for this one, very simple it is that for this one ds is equal to, you have to say consider all the conductors having the same radius, right. Therefore, you consider for example this conductor. So, ds will be is equal to r dash into that distance from here to here is 2 r. So, it will be 2 r and distance from here to here is again 2 r into 2 r. Look, for this conductor it will be r dash, but rest it will be 2 r 2 r. Please do not make it 2 r dash into 2 r dash, then it will be wrong, right, in to the power 1/3, right. So, ds will be then r dash is equal to 0.7788 r, that we have seen before, right, and if you simplify this you will get ds is equal to actually 1.46 r, the simplest one, but you see this kind of configuration. Now, second one is that you have 4 such conductors, right. So, all the conductors having the same radius r, right. So, in this case you have to find out ds, right, the geometric mean radius. So, consider for example this conductor. So, it is r dash, then distance from here to here this conductor is 2 r, then distance from here to here this conductor is also 2 r, and distance from here to here these two conductors is 2 root 2 r, because this is 2 r, this is 2 r. So, take the diagonal one. So, it is square root of 2 r square plus 2 r square, that will become 2 root 2 into r to the power 1 by 4. So, r dash is equal to 0.778 r. So, 0.778 r. So, this one will be r to the power 4. So, 0.7788 into 8 root 2 into r to the power 4 to the power 1 by 4. Therefore, ds is equal to 1.722 r, right. So, this is that this is your what you call, this is the answer, that geometric mean radius if it is 3 configuration, and if the configuration like this, and if the configuration is like this, right. So, next another example we will take, and after that we will go to the next chapter, right, next topic. So, for example, you take this one, first you see the problem, a 3-phase untransposed transmission line and a telephone line, I will show you the figure on the right side later, line are supported on the same towers and shown in figure 20, right, here it is, I will explain later. The power line carries a 50 hertz balance current of 150 amperes, magnitude 150 ampere per phase. The telephone line is located directly below phase C. Find the voltage per kilometer induced in the telephone line, right. This is the problem. Now, this is that your 3-phase untransposed line. So, the horizontal configuration it is A, B, C, these 3 phases, distance between phase A and B 4 meter, B and C your 4 meter, and A and C will be automatically your 8 meter, right. And the telephone line is there below the your what you call that phase C conductor, right. So, it is given here, the telephone line is located directly below phase C. So, it is below phase C. So, it is symmetrical. So, this is T1 T2 telephone lines, right. So, between these two lines distance is given 1.2 meter, right. That means, from the center point to this one is 0.6, this side is 0.6, right. Accordingly, you calculate the distance because you have to calculate dB1, dB2, dA1, dA2 all the distances. right. So, here to here distance is given for your 4 meter, right, this distance is given. So, therefore, this 0.6 meter actually this 0.6 meter actually this is 0.6, right. So, naturally this distance will be 4 minus 0.6, that means it is 3.4 meter. So, because you have to calculate dA1, dA2, dB1, dB2. Therefore, dB2 your dB2 is equal to 4.6 square plus 4 square, this is your dB2, right. So, if you take from here to here it is 4.6 and from here to here it is a right angle triangle. So, here to here it is 4 and from here to this point, I mean this point, right, this point. So, it is your 4.6 because this is 4 and this is 0.6. Therefore, you can calculate this 6.096 meter. Similarly, you calculate dB1. So, here to here it is 3.4 and here to here it is 4. So, under root 3.4 square plus 4 square. So, here is equal to 5.25 meter. Similarly, if you calculate dA2 from here to here. So, from A to C it is 8 and this is 0.6. So, it is 8.6 square and this vertical is 4 square. So, it is 9.484 meter, right. Similarly, dA1 you can calculate. dA1 as soon as you will calculate up to this it is 4, from here to here it is 3.4. So, total from here to here it is 7.4. So, under root 7.4 square plus vertical is this is given 4. So, it is plus 4 square is equal to 8.441 meter. So, all these distances are calculated. So, you have to calculate first all the distances, right. Once it is done, then from figure 20 this is your figure 20. From figure 20 the flux linkage between conductors T1 and T2 due to current conductor T1 and T2 means there is telephone lines conduct, right. Due to current IA is that same formula you will use lambda 1 2 the flux linkage, right, between conductor T1 and T2 in bracket IA is written, it is due to current IA is equal to the same formula 0.4605 into IA into log dA2 upon dA1 milliweber turns per kilometer, right. Similarly, this is your dA2 by dA1, right, and due to the current IA, right. Similarly, the flux linkage between conductors T1 and T2 due to current IB, this is that this conductor is in phase B carrying current IB. So, it is also lambda 1 to the flux linkage between your conductors T1 and T2 due to current IB is equal to 0.4605 into IB into log dB2 by dB1, right, milliweber turns per kilometer. Now, next one is since DC1 is equal because this DC1 that means this distance and this distance, that means C to T1 and C to T2, if we call C to T1 DC1 and C to T2 DC2, these two distances are same, right. Therefore, that since DC1 is equal to DC2 lambda 1 I2 IC will be 0, because in that case it will be log DC1 DC2 upon DC1, but as DC1 is equal to DC2, so it will be 0. So, directly we are writing that lambda 1 to IC is equal to 0 from the symmetry only, this because from here to here and here to here the C to T1 that is DC1 and C to T2 DC2, these two distances are same, therefore, it is 0, right. Therefore, total flux linkage between conductors T1 and T2 due to all currents is, right, total flux linkage. So, what you will do? You sum it up all, right. Therefore, total flux linkage lambda 1 2 is equal to lambda 1 to IA plus lambda 1 to IB plus lambda 1 to IC. Lambda 1 to IC is anyway it is 0. Therefore, you substitute these two expression, that lambda 1 to IA is equal to and lambda 1 to IB is equal to these two expression you substitute and lambda 1 to IC is equal to 0, right. Therefore, it will be 0.4605 in bracket IA log dA2 upon d1 plus IB log dB2 upon d1 milliweber turns per kilometer, right. Now, for positive phase sequence take IA as a reference. Suppose you take I A as a reference, therefore, I B will be equal to I A angle minus 120 degree, not showing the phasor diagram I A, I B, I C, because earlier we have seen. So, it is understandable, right. So, I B is equal to I A minus 120 degree for balanced system, right. Therefore, here you substitute in this expression I B is equal to I A angle minus 120 degree. Then lambda 1 2 is equal to 0.4605 I A log dA 2 upon d 1, then instead of I B we put I A angle minus 120 degree. So, I A angle minus 120 degree log dB 2 upon dB 1 milliweber turns per kilometer, right, is equal to that you take I A common. So, lambda 1 2 is equal to 0.4605 I A in bracket log dA 2 upon dA 1 plus 1 angle minus 120 degree log dB 2 upon dB 1 milliweber turns per kilometer, right. So, this is the expression, although you know the distances dA 2, dA 1, dB 2, dB 1 all are known to you, right. Next is that the instantaneous flux linkage can be given as lambda 1 2 function of t is equal to root 2 that mod of lambda 1 2 cosine omega t plus alpha. You assume this one that instantaneous flux linkage can be given us, right. So, it is root lambda 1 to t is equal to root 2 lambda 1 2, because we are assuming this lambda 1 to magnitude whatever will come, this is RMS value. Therefore, root 2 multiply, so it will be the peak value, that is why multiplied by root 2 cosine omega t plus alpha, this way you take. Therefore, the induced voltage in the telephone line is that V is equal to d of dt ddt of lambda 1 to t. You take the derivative this thing with respect to time for the you take, that is the voltage expression. So, is equal to minus root 2 omega mod lambda 1 t sin 1 2 sin omega t plus alpha volt per kilometer, right. You take the derivative of this equation. Therefore, V is equal to, you can write root 2 omega mod lambda 1 2, then this minus sign is there. So, this one we can write instead of sin omega t plus alpha, we can write cosine omega t plus alpha plus 90 degree volt per kilometer. This way you can write. Therefore, V RMS we can write that root 2 will not be there now, right. If you write V RMS, then omega mod lambda 1 2 and angle is alpha plus 90 degree. So, angle alpha plus 90 degree volt per kilometer. I hope you have understood this, right. Therefore, actually whatever you are getting here, this is basically your RMS value, RMS value, right. And then you for instantaneous flux link, the way you do for voltage or current RMS value to translate into instantaneous current or voltage, same thing, right. Therefore, your V RMS is equal to omega mod lambda 1 to alpha plus 90 degree volt per kilometer, right. Now, lambda 1 2 you substitute in this expression that dA 2 dA 1 and dB 2 dB 1 all you substitute. If you do so, then it is 0.4605 into IA. IA magnitude is of the current is given 150 ampere, and we have taken IA is the base, right, reference. So, therefore, it is 150 angle 0 degree, this way you write into log. Then D, all these distances are calculated, dA 2 is 9.484, right, dA 2 9.4 and dA 1 8.41 plus your first I am writing this one, the dB 2 6.096 and dB 1 5.25 into 1 angle minus 120 degree milliweber turn per kilometer, right. Then if you simplify this one, it will be lambda 1 2 is equal to 4.112 angle minus 70.6 degree milliweber turns per kilometer, right. So, this is at the RMS value, this magnitude, and this is the angle. Therefore, so initially you assumed that cos omega t plus alpha lambda 1 to this is that initial value you assume, no, omega t plus alpha, that means your alpha actually is equal to minus 70.6 degree, right, and mod of lambda 1 to magnitude, that RMS value 4.112. It is milliweber turns per kilometer, but not writing here, that understandable, right. Therefore, V RMS will be omega mod lambda 1 to angle alpha plus 90 degree, because this one your this expression of RMS voltage we got omega mod lambda 2 angle alpha plus 90 degree volt per kilometer, right. Therefore, this it is a 50 hertz system. So, omega is equal to 2 pi f, 2 pi into 50, mod lambda 1 is 4.112, then alpha is equal to minus 70.6 degree plus 90 degree. It is milliweber this thing into your 10 to the power minus 3, because milli term has been made it to 10 to the power minus 3. This should be volt per kilometer. After then V RMS actually is equal to 1.291 angle 19.4 degree volt per kilometer, right. So, this is your answer, right. Okay, before going to this, right, then I mean inductance, I brought few more examples, but time will be limited. So, many examples later will when you will learn this, we will give you many examples to solve, and hopefully the many interesting problems will give it to you, right. So, next we will move to that your transmission line capacitance, right, transmission line capacitance. So, those this capacitance of transmission lines, as you know, the transmission line conductors exhibit capacitance, right, with respect to each other due to the potential difference between them, right. So, this capacitance together with conductance forms the shunt admittance of a transmission line, but as I told you earlier, the conductance actually is the result of a leakage over the surface of insulators, right, and is very much negligible. So, conductance we will not consider, right. And third thing is, when an alternating voltage is applied to the transmission line, the line current capacitance draws a leading current. You know that capacitor draws a leading current, or in a power system later we will see in a power system that you will find that shunt capacitors are used, right. So, basically it injects reactive power into the your transmission line, right. So, later we will see that. So, generally what this thing or what you call that our objective now to calculate the capacitance of transmission line for single phase line to line capacitance as well as line to neutral capacitance. So, an electric field actually exists around a current carrying conductor, this you know, right. So, electric charge actually is a source of your electric fields, right. So, electric fields actually originate from the positive charges and terminate at the negative charges. This also you have studied from your higher secondary physics, right. So, the amount of capacitance between conductor is a function of your conductor radius, right, is a function of conductor radius and your what you call that spacing and height above the ground. So, these are the thing, but later we will see that effect of the height on the capacitance, right, and later we will see. So, basically three things: conductor radius, spacing and height above the ground. So, by definition the by definition the capacitance between the conductors that you know is the ratio of charge on the conductors to the potential difference between them. These are known to you. For example, you consider this figure, that is it shows a long, this is your conductor, shows a long straight conductor. We assume it has uniform charge, right. So, assume your positive charge, you assume it is a uniform and positive charge, right, throughout its length and is isolated from all other charges, so that charge is uniformly distributed. That means, this I assume it has a positive, this conductor has positive charge and uniformly distributed, and near no other your what you call near no other conductors or not affected by any other conductor or any other electric field, right. So, it is uniformly distributed. So, around its periphery. So, in the electric flux lines are basically radial, right. So this is the thing. So, we assume this is your what you call, this is your conductor carrying current of course, and it has a charge, positive charge q, and uniformly distributed around its periphery. And in this diagram there are 2 points, one is x1, another is x2. From here the distance is d1 and from here distance is d2, right. Since and it is equipotential your surface, since the your what you call that it is equipotential surface is orthogonal to the electric flux lines, the equipotential surfaces are concentric cylinders surrounding the conductor. So, basically these are actually concentric cylinders, right. Their radius is same, their center is same, right. So, from the Gauss theorem we know that the electric field intensity at distance y, right, from axis of the conductor, that means any distance, here it is not shown, but any distance y you take from the Gaussian theorem, you can write that E y is equal to q upon 2 pi epsilon 0 y volt per meter. This is equation 1. So, this is a new topic. So, again equation number is starting from 1, right, where q is the charge on the conductor per meter length, y is the distance in meter, and epsilon 0 is the permittivity of the free space. You know epsilon 0 is equal to 8.854 into 10 to the power minus 12 farad per meter, and x1 and x2 are situated at a distances d1 and d2 from the center of the conductor. This is from the center of the conductor, x1 and x2, this is the distance d1 and this is the distance d2, right. So, this diagram keeping it here, right. Therefore, the potential difference between cylinders from position x1 to x2, from position x1 to x2, right, it goes like this, coming like this. The potential difference between cylinders from position x1 to x2 is numerically equal to the work done in moving a unit charge of 1 coulomb from x2 to x1, right. There through the electric field produced by the charge on the conductor. That means, here you have 1 coulomb of your unit charge of 1 coulomb, and you are bringing it, that is equivalent work done, right, or numerically equal to work done that you are bringing from x2 to x1, right. So, that is why I have written for you the potential difference between cylinders from the position x1 to x2 is numerically equal to the work done in moving a unit charge of 1 coulomb from x2 to x1, right. Therefore, this V12 that your voltage V12 from integration of, it will be d1 to d2, because this is from d1 to d2, right. When we are making 1 to 2 means that it is at that point your what you call at point x1, right. That is the 1 to 2, that V12 is d1 to d2 Ey dy is equal to d1 to Ey is equal to q upon 2 pi epsilon 0 y into dy. That means, V12 is equal to q upon 2 pi epsilon 0 natural log d2 upon d1 volt. This is equation 2. So, V12 actually is the voltage at x1 with respect to x2. V12 is positive when q is positive, right, and d2 greater than d1, because if d2 greater than d1, this will be positive and q has to be positive, that is x1 is at higher potential than x2. If V12 is positive, then your x12, that is your what you call x1 will be at higher potential than x2. If it is negative, then x2 will be the higher potential than x1, right. So, that is your potential, your what you call that your voltage, because this voltage is necessary, because we have to find out the capacitance, right. So, that means, for alternating current V12 is a phasor voltage and q is a phasor representation of a sinusoidal charge. Now, potential difference in an array of solid cylindrical conductors. So, suppose this is that figure 2, right. Suppose that neglecting the distortion effect and assuming that the charge is uniformly distributed around the conductor with the following constants, that q 1 plus q 2 up to q n is 0, that is equation 3. That means, you have your q 1, q 2, right, then q k, q i, q m, q n, you have so many conductors up to n number of conductors, right, and distance is taken, for example, m to k is d k m, just opposite it is. If I move it like this distance is actually d k m, k to m, and here also I to m distance is d I m, right. So, this is the array of n conductors. Now, if you apply equation 2 to the multi conductor configuration as shown in figure 2, this is figure 2 and this is your equation 2, right. But now, you apply for that is for single conductor, but now you apply this one for multi conductor, right. Assume conductor M has a charge q m, this is the conductor M has charge q m, right, this is M, charge has q m, right, coulomb per meter. Therefore, the potential difference V k I, right, due to q m, that is V k I, this is k, this is I, the potential difference is here I have marked some plus minus, right, V k I due to the charge your q m, right, that equation will be that between due to the charge q m alone, right. So, that is why I am writing V k I in bracket q m is equal to q m upon 2 pi epsilon 0 ln d I m upon d k m volt, this is equation 4, right. So, this is that this equation we are writing from equation 2. Now, where k, when k is equal to m, if k is equal to m or I is equal to m, then d m m will become r m, right. When either k is equal to m or I is equal to m, at that time d m m will be the r m m, that is radius of the mth conductor, right. Now, if you use, now you have to, there are n number of conductors, so you have to apply superposition. So, using superposition, the potential difference between conductors k and I due to all charges, right, due to all charges will be is V k I is equal to 1 upon 2 pi epsilon 0. Now, all these things putting in sigma, that m is equal to 1 to n, you have n number of conductors. So, m is equal to 1 to q m ln d I m upon d k m volt, right. So, this is equation 5. So, things are simple, this is the most general one, right, and this one, this k to I, when you do V k to I q upon 2 pi epsilon 0, right, and some plus minus polarity I have shown, right, it equal to natural log d I m, that is d I m by d k m, right, this much of volt. So, this formula, right, is your what you call is generalized here for n number of charges, right. So, thank you.